Hello, everyone, and welcome to our presentation. My name is Janine Donnelly. I am the manager of webinars for IBM Systems Magazine, and I will be the moderator for today's event. Today's webinar, Discover the Cloud and Scale-Out World of Ubuntu on IBM, is sponsored by Canonical. Today's featured speakers are Dustin Kirkland, Anirban Chatterjee, and Adam Jollins. Dustin Kirkland is part of Canonical's Ubuntu product strategy team, leading the technical strategy, roadmap, and lifecycle of the Ubuntu Cloud and LOT commercial offerings. Dustin is an active core developer on the Ubuntu Linux distribution and maintainer of more than 20 open source projects. Adam Jollins has been working on open source strategy and marketing at IBM for 15 years, including both Linux and KVM. He is currently working on portfolio marketing for IBM's Linux One system, where he's helping to bring together next-generation applications and enterprise computing. Anirban Chatterjee has been a member of the Power Systems team at IBM for over 15 years. He started as a Linux developer, writing software for the firmware functions that assure system operations and resiliency before moving to more client-facing roles. Today, he is a portfolio marketing manager for big data and analytics solutions on Power. With over 70% usage in public clouds, Docker, scale-out workloads, and large Openstack deployments, today you'll see why Ubuntu is the choice for the next generation. With our introductions complete, Dustin, I will turn the presentation over to you.
Thank you, Janine. I'm very proud to be here today with my colleagues at IBM, and I hope we can introduce Ubuntu to perhaps some IBM partners that may not be as familiar with Ubuntu as other options on IBM System Z and Power Systems. I'd first like to show you that Ubuntu has tremendous traction in the enterprise. We've been building Ubuntu for over a decade now, 12 years in fact. We've just released our Ubuntu 16.04 LTS, and with Ubuntu we have seen Ubuntu adopted in an innumerable number of enterprises, and especially in the last few years on the real scale-out workloads like Uber, like Instagram, like Lyft. These are technologies that are really born in the cloud, and they started with Ubuntu from day one. We've also seen a bit of an enterprise shift of some traditional workloads in retail, like Walmart and Best Buy, as well as in the finance space, like Bloomberg, that have moved toward Ubuntu in the interest of what I think you'll see in the rest of today's call. That enterprise traction is closely tied to our very predictable velocity in Ubuntu. We've released Ubuntu on time, every time for 12 years now. We release an Ubuntu LTS, a long-term support enterprise release of Ubuntu every April of even-numbered years. So just last week we released Ubuntu 16.04 LTS. That LTS version of Ubuntu is a long-term support release because we'll support it for 5 years. Now, we also release interim releases of Ubuntu. We call those our developer releases. Those happen every 6 months. Every April and October, we release an Ubuntu developer release. In that developer release, we snapshot the entire world of open source software, run an incredible series of quality assurance tests, and produce that as a final GA image that many developers pick up and run as their desktop and their server platform as they're building the next scale-out workload. What we see in the enterprise, though, is a real concentration on Ubuntu as an LTS, or the Ubuntu LTS as the basis for production workloads. That predictable velocity is also coupled with unmatched choice. What we're going to see on Power and Z is that we've brought this unmatched choice to the IBM Power and Z systems, and that's really important. We take over 20,000 open source packages, snapshot those, test them, integrate them into our distribution of Ubuntu every 6 months, and then put a real focus on quality for those LTS releases every other year. Now, that choice also comes in the form of containers. Containers are an extremely important concept in all server labs that I've seen in the last couple of years. There are really two types of containers, and both types of containers are natively supported on Ubuntu. Of course, you have Docker containers, which are effectively application containers. Containers that include one and only one application in each very small, very portable container, and that's really Docker. We're going to see Docker running on a System Z, on an IBM System Z mainframe. But we also have this concept of machine containers, and those are handled through something called LXD. LXD is a hypervisor built on top of Linux containers, and inside of LXD containers, we see what amounts to a full machine. LXD is a much faster, lighter virtual machine than, say, VMware or KVM or Zen. For Linux on Linux workloads, we can actually dedupe the entire kernel out of the system and only run a single kernel across all containers. We've run thousands of containers on an IBM Power machine, and we've seen tens of thousands of containers, LXD containers, on an IBM System Z machine.
So we talked a little bit about this yesterday, about LXD and also Docker. And a lot of people out there are still running traditional virtualization as well. Can you talk a little bit about, why someone would choose to go with Docker, go with LXD, go with standard virtualization? Like, why would they pick one route over the other? Because I'm sure people on the call are still trying to figure out what the right path is for them.
That's a great question, Anirban. So there is a real difference between when you would use a Docker container and when you would use a LXD container. Docker is one of those technologies that's really born in the cloud. It's a technology that's merely a couple of years old, but has seen tremendous growth, tremendous adoption, and it's really tightly coupled to the concept of a microservice architecture. A microservice architecture is a new way of building scale-out apps. If you're a truly scale-out app like a Netflix or an Uber that is built around a bunch of microservices. There's the I want to reserve my car service, and I want to rate my driver service, and I want to cancel a reservation service, and let's scale that out to several hundred different applications, each of which may have its own developer working on that small piece of the workload. If that application is being born today, it's quite often architected in this microservices architecture manner, where each of those applications fit inside of its own Docker container, and then that Docker container is scaled out. Now, there's another set of workloads, the Linux on Linux workloads that I mentioned. We see these in environments that have been early adopters of cloud. They've been doing cloud or cloud-like things for 10 or maybe even 15 years with early virtualization. We're seeing a lot of those workloads that run today in traditional virtual machines, VMware or Zen, sometimes KVM, where if that workload is truly a Linux on Linux, not a Windows on Linux or a Linux on Windows, but really a Linux on Linux workload, we can get 10 to 20 times as many LXD machine containers on any given physical hardware as using a traditional virtualization. So that 10x compression can really save operations, save quite a bit of cost. But we also see, and this is the part that's really at the heart of LXD machine containers, is that the processes running inside of that machine container are running with bare metal performance. They're running literally on the bare metal in the host kernel. They're not escaping out of a virtualization layer and to execute on a CPU. And finally, the important abstraction is that a LXD machine container looks just like any other virtual machine. It actually boots, which is very different than a Docker machine. Inside of a Docker container, there's only one process. That might be the Apache or the MySQL process. In a LXD container, the first process, PID1, is sbin init, the usual Linux boot process, System D in this case, which then forks off a number of other system processes like SSH or syslog, basically the components that you would expect in any running operating system. And that makes it quite a bit more manageable from a machine perspective. You can use the same tools you use to manage other machines like Chef or Puppet or Ansible or Juju.
So if you have a consistent environment of Linux running everywhere, it's actually a really good way to eliminate waste and improve efficiency in your cloud, right? Because you don't have all the extra memory being taken up for stuff that's
right. You can dedupe your memory, all of those copies of the Linux kernel running, you can dedupe down to the one on the host. All of those copies of the underlying file system, you can dedupe and use ZFS, for instance. We'll see actually copy on write, and then we can we can treat them like virtual machines still and live migrate from one system to another.
That's great.
So built on top of application and machine containers are your truly scale-out platforms. We're here at the Openstack Summit in Austin, Texas. We took a quick break from the busyness around that conference to step into a conference room and take this webinar. But Openstack is a scale-out infrastructure as a service platform. Other platforms that solve slightly different problems but are very common in that they are scale-out platforms include Hadoop and the Hadoop family of big data. We've got a fantastic demo on top of OpenPower here we'll see in just a minute. In the PaaS space, the platform as a service space, Cloud Foundry is a PaaS that sits on top of now IBM platforms and can sit on top of OpenStack. And then for scheduling and scaling out containers, we've got both Kubernetes and Mesos, and we've brought essentially all of this to the Power platforms. In our demo, we'll show on OpenPower here in a second. We're running both Hadoop and Mesos on those OpenPower systems. Now, from an Ubuntu perspective, we're very keen on bringing and delivering the best of the open source world from connected devices, the smallest IoT type devices, and here we're talking about thermostats and wireless access points. All of this sort of boom of smart things connected to the internet, streaming important information. And where's that information going? Well, they're going from those connected devices to some of the largest hyperscale supercomputers in the world, and we're thrilled to work with IBM on helping deliver the back-end platform there. From an Ubuntu perspective, we have released Ubuntu 16.04 on 7 different architectures. That's 32-bit and 64-bit ARM, from the smallest Raspberry Pis to some of the 64-bit ARM embedded network switches, to the usual Intel 32-bit and 64-bit processors that you might find on laptops and desktops and very small servers, to 32-bit and 64-bit Power PC 64 EL being our very specific Power 8 focus, and now to the largest IBM Linux One mainframes, the System Z mainframes, and the Linux One that we're really excited to work with. We're also going to see a demo of Linux One here in just a second.
So I wanted to ask you about something that has come up a couple of times during, you mentioned we're at Openstack Summit, right?
Right.
And I know that your boss, Mark Shuttleworth, has been talking about big software a lot at this conference.
Yeah.
That seems really applicable to hyperscale data centers, right? So maybe you can talk a little bit about how big software is changing the way we deploy software.
Yes, and to do that, I'm going to scroll back just 2 slides where we were talking about the scale-out platform. So big software is it's sort of a new term. It's a new concept, but hopefully some of the people on this call will find it very, very poignant and relative to the work that they're doing here today. I think now, a couple of years later, most of us understand big data. Big data is really data sets that are too big to fit on any one computer or really any one rack of computers. It really takes an entire data center to store big data. And then there's also the processing of that big data. In our OpenPower demo, we're going to see some of that big data being processed. But the important point about big data is that the data is really the easy part once it exists. It's more about the management and the scale and the insight and the analytics that are required to make that big data useful. Let's draw that parallel now to big software. We're now seeing software that's too big to run on any one computer, any one system. And on this slide, we see at least 5 examples of software that's too big to run on any one system. I'm sure we can set up a developer environment of OpenStack or Hadoop on our laptop. But for a truly useful OpenStack or a truly useful Hadoop or a truly useful Cloud Foundry, Mesos, or Kubernetes, we need more than just a single server or a rack of servers. We need data centers dedicated to running those and deploying those and managing those. And core to that management and that deployment is a tool that we've developed, an open source tool that we've developed in Ubuntu called Juju. And Juju we've made available, of course, on the Linux One Z mainframe as well as the IBM Power Systems as well. Juju is a service modeling utility that can take any of these scale-out applications and deploy those against bare metal, private clouds, or any of the public clouds as well. And it's the same model. You create the model first, and then that model gets deployed wherever the destination might be.
I mean, that's a really interesting concept. It really speaks to how the only way to remain agile when you're developing like this is to be able to pull in the components from 10 different sources, 100 different sources, be able to deploy them multiple times.
Absolutely. And latest and greatest,
It's impossible to manage unless you have the right management infrastructure and the right training, really, to do that, right?
Yes. And upgradability, I would say that, it's quite important, for any of these. We talk about Openstack a lot here this week at the summit. What's the most important feature in Openstack? What's the single most important feature to you? It's the feature that's in the next release, right? And so the single most important feature really becomes upgradability, the ability to go from any one version of any of these to the next version.
Right.
And that's really core and important to what we're doing here. So we'll make our way back to our hyperscale supercomputers. And at this point, I think we should talk a little bit about the IBM Linux One.
Okay, so thanks very much, Dustin. This is Adam Jollins from IBM, and we're really excited about Ubuntu being available on IBM Linux One and IBM Z systems. We see this bringing together two extraordinary technologies together, which really offers really new opportunities to our clients. What we're doing is we're taking the technology that's been designed for enterprise systems, for the IBM mainframes, which needs to be very reliable, very available, very secure, high performance. And we're bringing that together with the cloud software and Ubuntu and Linux and all the open source packages that run on those. But open source and Linux is being used for really serious enterprise tasks these days. So it also needs to run on highly reliable, highly secure, highly available, very scalable underlying hardware as well. And with 16.04 from Ubuntu, which has been available since last week, you can now run this on IBM's Linux One and IBM Z systems. Now, it's a different instruction set in terms of the processor, but with Linux itself being portable and the open source packages in Ubuntu having been ported across, and with many of the most important open source packages like OpenStack and Spark and Docker also having been ported across, this means it's very easy to move workloads between different platforms. So why would you want to do this? Well, there's some advantages that come from running on a really big computer. First is in terms of performance. Linux One and IBM Z systems uses the world's fastest commercial microprocessor. So this is running at up to 5 gigahertz. Okay? This means that the single thread, the single process is going to be running probably around twice the speed of other servers. In terms of availability, these systems have been built for 100% availability. So we've been measuring for a number of years. We're probably up to sort of 5 nines in terms of availability. And we've also got the capability to have these geographically dispersed, so have them in different locations but linked together. From a security point of view, with Linux One and Linux One Z systems, you're able to take advantage of the very tight security at a logical partition level. So we can take Linux One or Linux One Z systems, we can split it up into 85 logical partitions, and between those we can have very secure walls at the highest level of security. That's EAL 5+. And then within each of those logical partitions, we can run Ubuntu or we can run KVM with Ubuntu in, and so you can see how that then gives the ability in a multi-client cloud to be able to give really tight protection between different systems. From a scalability point of view, it's really interesting. Obviously, this is a big system. We've got up to 141 cores in Linux One, and this means that we can run thousands of virtual machines, and we can actually, in testing, we found we can spin up over 1 million Docker containers. And we can scale in two ways on the Linux One. We can do scale up through the virtualization, so all your favorite scale out packages can run on there in terms of different virtual machines. We can also scale up within virtual machines as well. So you get a sort of diagonal scaling, which you're able to then adjust to each of the workloads. And finally, in terms of integration, this can be used as a front end to your existing data, your systems of record. So having all these next generation applications able to access the back end data, as for example, a bank doing online banking will be able to do. They want a really fun front end and useful and easy to use front end, but that's able to access the customer account data held on the systems of records. So we see this as being an amazing combination with Ubuntu being available on Linux One, Linux One Z systems. We've been running a beta test for the past month with a number of clients. One of those, L3C, which is a UK-based managed service provider, their comments were that their clients, since they're a managed service provider, want an environment that's flexible and cost-effective, whilst also meeting the highest standards for reliability and security. And they see Ubuntu on IBM's advanced enterprise systems helping to meet those needs, because developers can quickly deploy new applications to the cloud while having confidence the underlying system can handle fast-changing market demands. And so just finally on this slide, you probably heard us talking about both IBM Linux One and Linux on IBM Z systems. Both systems are based on the same technology and on the Z processor. IBM Linux One is specifically designed as a Linux-only system, so we're aiming this at new clients and new footprints, and it uses virtualization with Ubuntu Linux running them within those virtual machines. You can also add Linux to an existing IBM Z systems with Ubuntu, and you might want to do that if you wanted to take existing systems of record and data and provide next-generation applications as the front ends. So with that, I'll hand back to Dustin to show us something really interesting.
Thank you, Adam. Yeah, so we'll spend the next couple of minutes looking at a live Linux One demo. You can, hopefully you can see my screen at this point, and we are now on a command shell. This is a Linux command shell on a System 390X processor, of course. This is running Ubuntu 16.04, the latest and greatest bits. It's fully up to date. This is one of those systems and that we're very proud of to work with IBM on, where uptime is absolutely critical. Performance is absolutely critical. What I want to show you is a set of packages that we've made available on the Linux One and demonstrate that this really has parity with all other architectures in the entire Ubuntu fold, those other 6 architectures that we're talking about. First of all, I want to look at how many source packages are available on the system. And so there's a little utility inside of Ubuntu that will download the package list and count how many unique packages are available. And we'll see that all of Ubuntu on the System 390X is built from 29,956 different open source projects. And each of those projects may build one to many different binaries. We call those DEBs in the Ubuntu world, sort of like RPMs in the Red Hat world. Some of those are architecture independent, things like Python scripts and Ruby scripts, but many of them are compiled C binaries or Go binaries. And we'll see that on the Linux One, Ubuntu on the Linux One, there are 51,523 binary packages available for the System 390X architecture, and that's essentially identical to the same numbers on other architectures, Intel and ARM and Power, for instance. Here I want to show a couple of other things. We mentioned Docker. We can run ourselves a Docker container here. We're going to run an Ubuntu Docker container. And as fast as I can type that, I'm now inside of a Docker container. And inside of this Docker container, I could do something like an apt update, and I could install Apache or MySQL or MongoDB or any other sort of modern workload. I could upgrade this container. I could snapshot this container, move it over. I could export this container to a Docker file, and then recreate this exact container on another system. I also mentioned LXD. So if I run the LXC list command, I can see I have a couple of LXC containers already running. I could launch another one, but we'll just drop into this one. So I'm going to exec into this container bash. And now I'm inside of a container, which is inside of a System 390 machine, and we've got a couple of them running. What's really interesting about this container, this machine container, is it looks like a machine. It has its own IP address. It has its own processor space, or multiple processors, 4 in this case. It has its own memory system. But more importantly, it has a process tree that looks just like a process tree on the host. So it's running sbin and init, it's running a journal, it's running cron, it's running syslog, it's running at. I can snapshot this container, restore it, move it around. I can network them, and have multiple containers talk to one another. I'll exit out of this container though, and take a look at in this split over here on the right some of the libraries and utilities that a developer might use. Of course, we've got the latest and greatest GCC toolchain, so I can compile our hello world.c and execute our a.out and observe that we've got a binary, an ELF binary, running on an IBM System 390, and this really is a version of GCC that is truly latest and greatest. It's GCC 5.3, the exact same GCC version on all other architectures for Ubuntu. I could also run a really new utility like Go. Many of our newest technologies in the cloud world, like Docker, like LXD, like Kubernetes, are all written in Go. We actually have a Go tool chain for System 390 that we've worked on with IBM, and now we're running Go code, in fact. And if we look at the Golang package, we can see that we're running Golang 1.6. And then beyond that, those are compiled languages, but we also have the latest and greatest of the scripting world. So if we want PHP 7, by the way, which just released a matter of a few months ago, we can run PHP code, and we can host PHP applications here on a System 390 machine. Of course, Perl, latest and greatest Perl. We've got Python, Python 3, and Ruby as well. What we'd really like to show here is that we've brought the best of Ubuntu, the best of the open source world, and made all of that available on a Linux One on the System 390 platform. We're really quite proud of it. This is truly a modern scale-out operating system that's been used, if you saw that first slide, in some of the largest scale-out web workloads in the world. We can do all of that on System 390 now.
It's interesting because, people think of System Z, of Linux One, of Power as being completely different systems that are almost alien to the x86 ecosystem. But what you've done here is you've really offered a commonality of toolset, a commonality of interface, a commonality of apps and programs that are available, so that you can really just pick up and go on any platform you choose, which gives you the freedom to choose the right platform for the job.
Absolutely. Right? For the app developer, the person writing C, Python, Perl, Ruby, Go code, they don't need to know anything at all about the underlying system. The administrator who's standing up the Linux One box, assuming there's a team that's responsible for the hardware, right. They may need some Z knowledge, but the developer is any other Linux developer. And we've seen, especially with Microsoft's embrace of Linux lately, we've seen that the Linux developer is truly the scale-out developer, the developer writing the next generation of code for the world.
Right. And we'll talk about Power in a second, but I know that Mark made the point earlier, I think yesterday, in the session, that people want to put these new apps close to their SOR data, right?
Right.
Their key enterprise data, which is why it's so important to have it on Linux One, right?
That's right. Absolutely. So let's talk about power.
Yeah, sure.
Button.
So, and I know that, Dustin, you've been very involved in this from the beginning. I know Ubuntu and Canonical have been strong partners of ours for a while I think we've all sort of realized together that there's a gear shift happening in the data center, right? There's a change happening in how people in hyperscale data centers consume IT, and we also expect that change to ripple down to the enterprise data centers, right? And that change is basically that people they're not going off and buying off-the-shelf systems anymore. They're actually looking to innovate within the systems themselves, within the hardware, within the actual platforms, to find new ways to eke out extra efficiency and extra performance from the data center, right? You'd agree that that's a huge trend.
Absolutely. I think you're proving that right here.
Yeah, absolutely. I mean, if you look at a chart that's on the screen right now, you'll notice that we've got Moore's Law, which everyone on the call probably knows quite well. But, you'll also note that, of late, it hasn't really been keeping up with trends of the past because they haven't really been able to push the performance of each individual x86 processor at the same rate they've been able to in the past just because of physics. Right? So in order to keep that improvement of performance into the future, the only way to bring that level of performance improvement forward is to innovate in other parts of the stack, not just the processor, right? But also the firmware, the accelerator software, the storage, the network layer, right? Being able to innovate in all of those spaces is critical to being able to enable full stack acceleration into the future. And that's what these hyperscale data centers are really asking for. That's what Lawrence Livermore and Oak Ridge were asking for when they tried to develop their next supercomputer. They just announced I think it was the Oak Ridge supercomputer called Summit that just went live. And it's basically built on open power technology. It's running Ubuntu, right? But it's also running with power processor technology. It's running with Mellanox I/O technology and NVIDIA accelerator technology. And that's one of the key ways that we're delivering full stack improvements, not just in the process, but in the overall system, to enable Oak Ridge and also Lawrence Livermore to really do some very, very interesting and amazing things in the area of weather modeling, climate analysis, like temperature analysis, all the HPC workloads that they run over there.
Important stuff
that needs to run faster because there's so much more data to parse through, right? We've also got a trend with Open Power of actually bringing in more and more partners. We actually had about 200, I think over 200 partners that within Open Power. I think Ubuntu was one of the founding members, right?
That's right.
And it's because of this trend that we see, this change that we see in the data center. One of the biggest surprises that I had when I was at this conference, at Openstack Summit, was how many questions we were getting. We actually had a Power8 box in our booth, and we were showing off the Power8 box, and we actually had a GPU accelerator in there. And we were getting tons of questions from OpenStack developers about the GPU, which surprised me. I was expecting it mostly to be about management or just ease of deployment, but a lot of people are really interested in what they can do with the GPU, and the reason they're interested is because Power has made it really easy to leverage accelerators. They're a full-fledged part of the system. They're not shuffled off into the I/O layer. You don't have to go through an I/O bridge to get to it. It's actually part of the processor fabric, and so it's much easier to code for, and it's much easier to actually get the performance out of it. Now, a lot of developers have been interested in that. So we've actually published a number of benchmarks already showing about 2x the performance per core on Power8 compared to x86. We're actually making Power8 available to our customers in a number of new ways. We've had, for about a year now, lower priced one-socket and two-socket boxes that are priced pretty much exactly the same as the boxes you'd buy from traditional x86 providers, which means that you're able to buy, these 1U, 2U boxes and rack them and stack them just like you would any other machine. So there's nothing new to learn there. But you also get all the performance benefits of the per-core performance and also the I/O performance in the box. You get 4 times the memory bandwidth, 4 times the threading, and 4 times the processor cache on these boxes compared to x86. And that really translates to this 2x performance per core that we see on Power8 repeatedly. We also have innovations like CAPI, the coherent accelerator processor interface, that allows you to hook in accelerators with much less code and much more performance without having to worry about I/O latency. And what that really translates to is, a system that is really built for analytics workloads in the cognitive era. Like Watson is a great example of this, right? Apache Spark is another great example of this, where we've shown that with acceleration, you're able to deliver some really interesting things. And all of that is running on Ubuntu. So being able to offer that common interface, as you were just demonstrating a second ago, is going to be critical, I think, for our app developers who know Ubuntu, who know Linux, but need to be able to leverage these new technologies. And I think you're about to show a demonstration of how we're actually applying Power and Ubuntu to a new category of workflow called machine learning, right?
Right.
So why don't we talk about that a little bit?
Yeah, you bet. So we've got another demo that we'd like to look at here. This is a series of machine learning algorithms and data. We've actually got this public on GitHub. This is open source code. You can find it at the URL at the top of my screen now. I'll leave it here just for a second, github.com. It's my colleague Samuel Kozane, his GitHub account. He's got a deep learning demo that he produced here for the Openstack Design Summit, ODS-DL for deep learning. So in the setup, you can see he's got a number of colleagues that he's worked with here. What we've done here is essentially built an HDFS at the bottom layer, Open Power at the bottom layer. Let's not forget about the hardware. And then on top of that, a scale-out file system, a Hadoop file system, HDFS. Sitting on top of that, we're marshaling jobs using Mesos. Mesos includes a bunch of technology, but largely we're using it to schedule jobs out against a bunch of systems using containers, of course, and then you'll see the rest of the technology that's built around it. And using the GPU, that's extremely important. As Anirban just mentioned, the fact that Power exposes the GPU in a very convenient manner for developers, we're actually using the GPU to crunch these numbers. So Spark sits on top of Mesos and is helping derive some of the insight. And then Deep Learning 4J is an essential technology that we've also leveraged here, which is quite frequently found in the cognitive learning and the machine learning space. So with this, we have deployed one of those big software models that Anirban mentioned here, and you can see all of the pieces, and how they interact with one another. And you can see the logos for things like Hadoop and Spark, the NVIDIA GPUs, the deep learning and Spark, and then the logs that are ultimately ingested. So we're ingesting. At this point, I'm going to move to the graphical interface, the web interface. We're using some technology that we've been working on with some partners of ours called SkyMind. What you're seeing in that graph that's moving from right to left here, we're actually ingesting logs from multiple OpenStack deployments. So OpenStack is a big, complex infrastructure as a service. There's 20-something different moving parts, two of which are very important to us, and we have ingested here, Nova and Neutron. Both Nova and Neutron produce very verbose logging, and occasionally in that logging, you see things that you don't want to see, such as errors, in fact. So over here, we can see the log levels, and some things are informational, and some things are errors, in fact. Here we have the logs against Neutron, which is the networking component of OpenStack, and on this tab we have Nova. Nova is the compute portion of OpenStack. And using this data, we're watching these logs and applying some tailored machine learning algorithms to predict the time to live of services. And you can see in the far right column the time to live of these services. You can see whether or not that time to live is greater than or less than 60 seconds at this point. So we're still training the model, we're still refining the model, but when there is an error message, such as maybe this line I'll highlight, there is an important error message here that we need to be aware of, that the time to live of that service, the chances of that service going down in the next 60 seconds is actually an 88.3% chance. That's probably something that we would want to take a look at in the very near future. This entire demo is completely built on top of OpenPower. We're using OpenPower for its scale-out capability, for its GPU capability, and this is all Ubuntu.
And the reason to do this is because you're actually able to train the model faster, right?
Absolutely. So, deep learning and cognitive insight is all about feeding data, large amounts of data, into the algorithm, the system, deriving insight from that, and then actually operationalizing that knowledge to your benefit. So we run a lot of OpenStack clouds for our customers through a product we call Bootstack, where we manage their OpenStack remotely, right? OpenStack's open source. You can deploy it yourself. You can pay Canonical to deploy your OpenStack, at which point you can take it over, or you can take the fully chaperoned approach, and we will actually deploy the OpenStack and manage it over time. When we do that, we want as much information as possible about what's going on inside of that OpenStack, and things like this is giving us even more insight and more of an edge to help keep that OpenStack up over time.
Right, because all the different components are generating logs asynchronously, right? They're actually doing their own thing on their own time, and the trick is correlating something happening on one end of the data center with something happening at the other end.
That's absolutely.
And bring them together and say, okay, this actually indicates a problem.
Yes, indeed. Right. OpenStack being one example of that, but we could actually apply that to any of the big software. So Kubernetes is just as complicated as this. Cloud Foundry is just as complicated as this. And when deployed in production, a Cloud Foundry might span hundreds or thousands of nodes and have, sitting on top of it, hundreds or thousands of apps running there.
So what's the value of having the training model run faster on Power?
Yeah, well, the fact that this can be done in real time. There's another aspect here, which is intrusion detection, right? So intrusion detection is the sort of thing that you need to know about as soon as possible, and you need to take evasive action as soon as possible, right? And so being able to do that in real time rather than a week later or when you find out about it on Twitter that your service is compromised, I think you'd much rather have that insight in real time.
Very good. And do you think it's because of the threading? Is it because of the acceleration? Is it some combination of multiple factors? Like, what is it about Power 8 that makes it run so much faster?
That's a good question. I think you're probably in a better place to answer that question than me. I know the GPU is essential here.
It's the acceleration, I think, is what really gives it the edge, right? Because the acceleration allows you to share. The way we've done it on Power 8 is we've actually shared the memory, right? So the memory space is shared between the main processor and the accelerator. What you used to have to do is
shuttle DMA.
Right. You'd have to actually move data across the I/O bus with old accelerators, and that made them difficult to code for because you had to write the code to shuttle the data back and forth.
Right.
And that was often 20x the amount of code.
Okay.
Because of that. So because you've eliminated all of that data shuttling code, you're able to develop the accelerator much more quickly.
Right.
And that's how you get the efficiency.
Right. Okay. That makes perfect sense. So we can point straight at that data and save ourselves quite a bit of time by sharing it. Right.
Cool.
Great. So at this point, I think we can open this up to questions. I've got one for you, actually.
Yeah.
You mentioned Watson and Ubuntu in the context of Watson. Can you tell us a little bit about how Ubuntu is used in Watson?
So there's actually a lot of different products that are part of the Watson group. I'm not directly connected with the development, so I'm not really sure where all the components are right now. I know that they're moving to a place where the majority of the components are running on Power 8 architecture, which means that you'll be able to use accelerators, you'll be able to use the most advanced capability, and you'll be able to do all of this in the cloud. We actually also just moved Power 8 into software, which is where a lot of the Watson stuff is going to be hosted out of.
Right.
And so that means that when you've got Watson services hosted in the cloud, you'll be able to use accelerators to deliver real-time answers to questions using the open Power technology that Ubuntu is helping us develop.
That's really quite interesting.
Yeah.
I'll also say that here at the OpenStack event in the IBM booth, there's the Linux One with the bezel off, and the bezel looks awesome. But as a geek, I kind of want to see what's under the bezel, right? And so it's all plexiglassed away so that you can see straight through it. And it's really an incredible machine. It's beautiful from from a complexity standpoint, but an organization standpoint. The concept of drawers and cores in a drawer and IFLs, just the way that machine is partitioned is really pretty cool.
Yeah. So Adam, you probably know more about that than we do over here. I mean, there's a ton of design work that goes into placing all the components within the frame of the Linux One. Isn't that right?
Yeah, that's right. So it's been designed as a balanced system. So all the I/O is offloaded to specific I/O processors. The sort of the processors, CPUs themselves are in drawers. And with 1604, Ubuntu has introduced some really interesting pricing. I think it's $19,500 for a drawer full of cores or processors on the Linux One or on Linux on Z systems. So this is really competitive pricing with other systems, and we think it's going to attract a lot of people to using Linux on and Ubuntu on Linux One.
Yep, I'll reiterate that and say that we have priced Ubuntu on the Linux One very aggressively, and it matches that scale out workload. As much Ubuntu as you want to run, we're not counting the number of deployments of Ubuntu, the number of IFLs, the number of cores, the amount of memory, the amount of disk. It's as much Ubuntu as you want to fit in a drawer for 19K, for 19.5. That really matches what we've seen in other industries where counting Ubuntu or counting instances of Linux, it's just not practical when instances might live a matter of minutes, hours, seconds in some cases when it's a run-to-completion type batch job. Canonical will provide full support for those customers. Running Ubuntu will take support questions. We'll provide bug fixes. We'll provide security updates for as much Ubuntu as you can pack in a drawer, and we've seen in our benchmarking that amounting to hundreds, perhaps even thousands of VMs and insane numbers. I saw all the way up to 1 million containers across an entire Ubuntu One, which consists of 4 drawers. Linux One. That's 4 drawers in a fully populated Linux One Emperor, right, Adam?
Yeah, that's right. Yeah, up to 4 drawers, and takes you up to 141 cores.
So we talked before about how you're offering a consistent experience with Ubuntu across all platforms, every single Power 8 machine that we make, all the SimZ and Linux One machines, and of course x86. And you also mentioned that you guys always release on time. So I know one thing people are probably wondering on the phone is what's the release schedule of Linux One and Power compared to traditional x86? Is it the same? Is there
absolutely identical? Absolutely identical. So we just released Ubuntu 16.04 LTS last week. I said that will be supported for 5 years. We expect to see. We've already seen thousands of Linux One virtual machines launched to date. We expect to see plenty more. We're already working on Ubuntu 16.10. Our next release of Ubuntu, we're in the planning phases for that now. We spend about a week or 2 at the beginning of the cycle reprioritizing, looking at the market, understanding what open source technologies that are just now emerging that we want to bring to the next release of Ubuntu. The engineers will get to work immediately and start cranking on Ubuntu 16.10. We'll spend 3 months developing it, and then we'll have a checkpoint. We call it a sprint in the middle of that. We'll all meet up somewhere in Europe in the summertime, checkpoint where we are, and then we will get back on the train and steamroll toward a 16.10 release of Ubuntu that will release in October. That 16.10 release will be followed by a 17.04, and then a 17.10, and then eventually an 18.04 LTS, so another LTS. Every one of those will be made available on both Power 8 and Z in perfect lockstep with x86. It's not a release x86 and then sometime later add support for other architectures. All of the continuous integration testing that we do at Canonical is done equally across all the platforms. We make available those test results and on publicly on our site as well, and you can track it over time.
And that's because it's all the same source code, right?
It is
the same code.
It's absolutely the same source code, the same build processes, the same testing and package testing that goes into it.
Yeah. I'll remind the attendees that you can submit questions at any time using the interface. While waiting for those to come in, I'll ask you. I mean, I told you what surprised me. What surprised you this week at Openstack Summit?
Wow. So I was actually at the first Openstack Summit in 2010, July of 2010. There were 75 of us in one conference room in the Omni. And this week there are 7,500 registered attendees. That's a 100x, a 100-fold increase in attendance from 6 years ago, less than 6 years ago. That's really what surprised me, is how fast Openstack has taken off.
Yeah, and as an Austin local, I'll tell folks on the phone, this is the same exact venue that they're doing South by Southwest Interactive. We just took over the building.
That's right.
So it's huge this year.
That's right.
It's been really amazing to see.
So at this point, I think we'll start to wrap up here. We have a couple of resources that we want to make sure that people have at their fingertips. We make sure that you try out Ubuntu on your Linux One, your System Z machines, your Power machines, and leave us some feedback. You can find information about Canonical's partnership with IBM at partners.ubuntu.com/IBM. The IBM.com Linux One site is available, of course, and there's a dedicated landing page for Ubuntu. You can go to either of those and download and run Ubuntu on both C and Power. And then, we certainly hope that you try this out, that you try apt and install some packages, that you try Juju, deploy some workloads, and we're really interested in seeing what the scale-out world can do with Ubuntu and IBM.
Hey, Dustin, it's Janine. We had just 2 more questions come in, and we do have a couple more minutes. So I'm going to run them by you, and,
okay.
We'll take it to the top of the hour. So please continue to submit your questions. Here, will it run on the ZBC12?
I'm going to pass that one to Adam. I'll say that we're running on the System 390X architecture, which is the 64-bit System 390. We're not targeting the older generation 31-bit S390 architecture. Adam, can you help with that particular question, the ZBC12?
The ZBC12, yes, we run on the ZBC12.
And these are all from different people. Interesting. Okay, how about this? Ubuntu on Power runs Power VC? Question?
Right. So the virtualization for Power is either Power VM or Power KVM, and we also offer Power VC, which is our orchestration software. It's important to know that you also have the ability to use any OpenStack software at all to manage your existing cloud on x86 as well as on Power. So you can use our own Power VC, or you can use your existing industry standard OpenStack compliance software as well to manage all of this stuff.
I'd like to comment on the question here about the Linux install experience. So the Ubuntu install experience, we are publishing ISOs, the .iso file that you would download and burn to a USB or a CD-ROM to install a traditional physical machine. You can, of course, download those same ISOs and run them on both Power and Z and tab your way through the install process. Of course, that can be automated with Ubuntu using something called DI, Debian Installer. But I will say that we're really excited to bring to this world of IBM the idea of live images. So we publish images for all of the architectures, and it's a far more cloud-like experience. You take that image is identical from the start. You simply run the image. You can skip the entire install process. It's an image that is identical that you can use over and over again for cloud workloads. And then we use something called Cloud Init. Cloud Init is an open source project that Canonical has led for quite some time to ensure that we can deliver the same Ubuntu experience in public clouds that now we deliver on hardware. Cloud Init has the ability to inject your SSH keys into the system. You can simply tell the system what your GitHub or Launchpad ID is if you publish your SSH keys there, or you can embed them literally into the metadata that feeds in. But Cloud Init is a fantastic way of giving an instance its own DNA at first boot and skipping the tabbed ISO install process, which can take quite a bit of time.
There's one here.
Yeah, so another question for you, perhaps, Adam. I'll answer as best as I can. Will Ubuntu run under ZVM on Z systems? That answer is yes. Exactly the demo that I ran here today was Ubuntu running inside of a Z VM. Adam, would you like to add anything to that?
Just that you've got a choice in terms of where you run Ubuntu in terms of virtualization, so you can run it bare metal within the logical partitions. You can run it under ZVM, or you can run it under KVM as well. So you've got the options there in terms of which virtualization technology you want to use.
Of course, and then once you're inside of Ubuntu, we showed that you can run Docker as well as LXD to further take that Ubuntu system and chop it up into containers. I'd like to remind everyone that the recording of the audio-video of this presentation will be available. There will be an email sent out after this presentation with a link to watch the recorded content. Slides we will make available as a PDF for download as well. I will post them. We'll certainly send them to everyone on this call through the email correspondence. I'll post them on my Twitter account in a few minutes. My Twitter ID is Dustin Kirkland, all one word. So at Dustin Kirkland, if you follow that, I'll send those PDFs out momentarily.
That's right. You can follow me at ANIRBAHN if you care at all what I think about anything ever.
This is Janine again. I would like to thank everyone for attending today's webinar, and I especially want to thank Dustin, Anirban, and Adam for sharing their expertise with us today. That follow-up email will come in the next couple of days, and that concludes our webinar. Thanks again, and have a great day.